Two cucumber plants were identical in every way until a single watering with yeast changed everything. By day 12, one outgrew the other so dramatically that the harvest was nearly triple. Scientists call it impossible. Garden logs documented it. But how could live baker's yeast trigger such explosive growth, and what is really unfolding underground within the first 48 hours? A gardener's logbook dated May 3rd records the start of a simple trial. Two cucumber seedlings, the same variety, were planted in the same bed, spaced a foot apart. The soil came from the same bag, the water from the same can, and both caught the same hours of spring sun. On planting day, one received a single drench, a mason jar of water, yeast and sugar mixed until frothy. The other received plain water. Every detail was tracked, from soil temperature to leaf count, in the margins of a spiral notebook. By day 12, the difference was impossible to miss. The yeast-treated plant had already produced a second flush of leaves, its stem thickening, while its twin lagged behind, shorter and paler. The log notes: yeast plant, 8 leaves, 2 runners. Control, 5 leaves, 1 runner. Photographs taped beside the entry show the contrast, a gardener's attempt to capture what words could not. Throughout the season, the notebook filled with numbers, flower counts, fruit set dates, harvest weights. When the vines finally tired in July, the results were tallied. The yeast plant yielded just over 3 times the total weight of cucumbers compared to its control. Not a handful more, but 3 full baskets for everyone. This was not a fluke from a single backyard. Extension agents across several states reported similar home garden trials, with some gardeners posting their logs and photos on citizen science forums. The pattern held: same soil, same sun, same water, only the yeast drench set the winner apart. For skeptics, the appeal lay in the experiment's simplicity. No special equipment, no expensive products, just a kitchen staple and a gardener's patience. The numbers and the photos left little room for doubt. Something in that single watering had rewritten the rules of the harvest. Beneath the surface, the story of that yeast drench unfolds in the darkness of the soil. Baker's yeast, Saccharomyces cerevisiae, when mixed with sugar and warm water, awakens from its dry, dormant state. Within half an hour, the solution turns frothy, a sign of living cells consuming sugar and releasing carbon dioxide. Once poured into the root zone, these microbes encounter a new world: tangled roots, moist soil, and a web of native bacteria and fungi. The first hours are a scramble for resources. In laboratory flasks at 30 degrees Celsius, Baker's yeast can double its population in about 90 minutes, a pace unmatched by most soil microbes. In a garden bed, where temperatures hover between 15 and 25 degrees and oxygen is patchy, the surge is slower but still dramatic. Studies using sterile soil microcosms show that after a single yeast watering, cell counts in the rhizosphere climb sharply over the first 24 to 48 hours. The yeast's appetite for sugar and oxygen lowers the soil's pH, triggering a cascade of chemical changes. Microbiologists tracking these changes with microelectrodes and DNA sampling report a distinct pattern. By hour 6, yeast numbers are peaking, and by hour 12, the soil around the roots is teeming with new life. The yeast does not act alone. Its byproducts, B vitamins, organic acids, and enzymes feed native bacteria, which in turn break down organic matter, releasing minerals that plants can absorb. This microbial bloom transforms the root zone into a hotbed of activity, with nutrients cycling faster than in untreated soil. By the end of the second day, the soil's chemistry has shifted. Oxygen levels dip, acidity rises, and the population of both yeast and friendly bacteria expands. These changes prime the roots for what comes next, a wave of signals and nutrients that drive new growth. The field logbook's numbers, more leaves, longer stems, find their explanation here in the invisible drama just beneath the surface. In a greenhouse lined with rows of young cucumber plants, Dr. Mateo Alvarez points to the roots beneath the soil. Here, the story of yeast's effect on plant growth takes a new turn. Activated baker's yeast mixed with sugar and water does not just feed microbes, it acts as a biochemical trigger. As the yeast population blooms, it releases natural compounds, including auxins and cytokinins. These are the same classes of hormones that plants use to signal root branching and cell division. Peer-reviewed studies from Wageningen and Minnesota confirm the pattern. Within 2 days of a single yeast drench, root tips begin to branch more aggressively. The effect is most pronounced during the early vegetative window, when seedlings are establishing their first root networks. In controlled trials, plants treated just once at this stage developed up to 30% more root mass compared to those watered with plain water. The hormone surge sets off a cascade. Roots spread wider, absorb more nutrients, and support faster shoot growth above ground. Dr. Alvarez explains that timing is crucial. The early vegetative phase is when roots are most sensitive to these signals. One well-timed application can launch weeks of accelerated growth, while repeated doses offer little added benefit. In practice, it is not about feeding plants more often, but about hitting the right window, using biology's own signals to unlock a plant's potential. Fermentation as a tool for boosting plant growth is not a recent discovery, nor is it limited to any one region. In the hills of Korea, farmers have relied on fermented plant juice, FPJ, since at least the 19th century. By mixing fast-growing weeds with brown sugar in glass jars, they captured the essence of living plants and microbes, then poured this solution onto their fields to spark new growth. Han Kyu Cho, a central figure in natural farming, brought FPJ and related methods into wider use through the Jatam movement, which emphasizes ultra-low-cost, do-it-yourself ferments made from local materials. These living brews are not just a Korean tradition. In Victorian England, gardeners steeped comfrey and nettles in rainwater, creating nutrient-rich teas that fueled cottage gardens through lean years. Across Eastern Europe, yeast-based ferments kept vegetable plots productive during fertilizer shortages, especially in the dacha gardens of the Soviet era. Despite their long record of success, these living solutions rarely appear on store shelves. The reason is simple. Active yeast and other microbes keep fermenting, releasing carbon dioxide that builds up pressure inside sealed containers. Bottles swell, lids pop, and the product spoils before it can reach the customer. Packaging regulations and safety standards make commercial sale nearly impossible. Meanwhile, the economics are stark. A homemade yeast solution costs less than $1 to make, while a bag of commercial fertilizer can run 30 to 50 times as much. The market wall is not scientific but practical. Living biology does not fit into a business model built on shelf-stable products. Across dozens of peer-reviewed studies and extension-led trials, the pattern repeats. Yeast-based solutions deliver measurable but not miraculous gains. On average, vegetable crops treated with a single well-timed yeast watering show yield improvements between 20 and 30% over untreated controls. This is not an outlier or a marketing exaggeration. It is the consensus of controlled experiments in greenhouses and home gardens alike. The numbers hold steady across tomatoes, cucumbers, beans, and peppers, with best results seen when the solution is applied early in the plant's vegetative stage. But these benefits come with caveats. Researchers caution that more is not better. Over-applying yeast, whether by increasing the concentration or repeating the treatment too often, can stress roots, disrupt the balance of soil microbes, or even attract unwanted pests. Extension Service safety guides recommend a simple rule: never use undiluted yeast in space applications at least 7 to 14 days apart. For most gardeners, a single diluted drench per crop cycle is enough to see the full effect. If you are new to this method, start small and test on one plant before scaling up. This approach not only protects your soil and crops, it also gives the clearest picture of what a living solution can truly offer. The promise is real, but it is rooted in biology, not magic. Today, the biggest breakthroughs in growing food don't come from a bottle. They come from living soil. As fertilizer prices surge and supply chains strain, the science is clear. Roots respond to biology, not branding. Sometimes, the oldest solutions are the ones we need most. What will you try next?